औज़ु बिल्लाहि मिनश शैतानिर रजीम बिस्मिल्लाहिर रहमानिर रहीम रब्बि इश्रह ली सदरी व यस्सिर ली अमरी वहलुल उक़दतम मिन लिसानी यफ़क़हू क़ौली सुब्हानल्लाहि वल्हम्दुलिल्लाहि वला इलाहा इल्लल्लाहु वल्लाहु अकबर वला हौला वला कुव्वता इल्ला बिल्लाहिल अलिय्यिल अज़ीम अल्लाहुम्मा सल्लि अला मुहम्मदिन व अला आलि मुहम्मद कमा सल्लैता अला इब्राहीम व अला आलि इब्राहीम इन्नका हमीदुम मजीद. Okay guys, so my today's video is about the physics of rolling of bodies of circular cross sections for the first time in Islamic history. Okay guys, you can see toppling or turning of a rectangle in this figure. We have a prismatic rectangular body with the rectangular cross-sectional area is sitting on an inclined plane, and we can see that the only force that causes this body to either to topple over is the component of the force of gravity. The force of gravity is acting like this towards the center of the earth, mg, and this component is the only force causing all sorts of motion in this rectangular piece. This is the only force responsible. Okay, so this mg sine theta, the toppling, let's suppose the sliding does not happen, the topple over happen, the body turns at this point. Let this point be called A. This point is A, and this rectangular body, it topples over here. When it topples over here, when we take the summation of the turning moment required to do is mg sine of theta, this force times this distance, which is h by 2 minus this. This is the resisting torque, the torque that resists the motion of topple or stops the motion of topple, in other words. So this is the resisting torque. This is also the component of the gravity, mg cos beta times b by 2. Like if this distance, if the width of the rectangular prismatic bar is b, then b by 2. So mg cos beta times b by 2. Now if this torque has existence, then it would be greater than 0, and the body will topple over. Okay, so the condition of topple over would be tau greater than 0 or beta should be greater than alpha over 2. Okay, now what is alpha? Alpha, when we have, in reality, when we have a circular cross section, then a small area gets in touch with the circle, gets in touch with the inclined plane, causing a small circular area of radius a. If it's a sphere, we will consider a ball rolling down, a spherical body rolling down an inclined plane. So we have a small circular area. Depending upon the elasticity of the two materials in contact with each other, there will be a small radius in millimeters or in centimeters, depending upon the elasticity of area A, circle of area of radius A in contact with each other in both regarding both the surfaces. Okay, so this will be A. So mg cos beta times A and mg sine beta times this distance. But here in this case, the area of contact is this surface, rectangular piece. If it's prismatic, then the rectangular piece. So the area, the distance, the moment arm is b by 2. So b by 2. Okay, so when we make it equal to 0, we see that beta should be equal to alpha by 2. Here, the distance, this is the radius, this distance is r cos alpha by 2, because alpha is this angle that the circular area subtends at the center of the ball, and the half of it is this. So this is the right angle triangle. So this is r, this distance is r cos phi by 2, and this is r sine phi by 2. This distance r sine alpha by 2. So a, so small a, you can call it small a, or you can call it r sine alpha by 2. So r sine alpha by 2, r cos alpha by 2. So tau is this. So when tau is greater than 0, then we have the condition of rolling. Beta is greater than alpha by 2. So this is the condition of rolling. Like we had previously in my previous video, we had the condition of sliding. Mu is greater than tan inverse, beta is equal to tan inverse mu. If beta is greater than tan inverse mu, then sliding will happen. So you can check my previous videos. Okay. Okay, so here is the, you can solve this one too, but I don't, eventually I'm going to do a spherical ball, so I don't want to focus here. Okay, this is just preliminary, starting, just a starter. Rectangle is just a starter. Okay, so this is toppling or turning of a rectangle. Okay, figure 4.2.7 shows the forces and torques involved in the process of toppling or turning of the rectangle. Rolling is basically toppling at each movement of the object going down the slope. Okay, so guys, this is the gist of the story, is the main matter, is the essence, that rolling is basically toppling at each movement and every movement of the object going down the slope. Objects with circular cross sections roll by continuously turning or toppling at each moment. Okay, like here you can see triangle, square, pentagon, hexagon, heptagon, octagon, nonagon, decagon. So eventually you see what is rolling. Rolling is basically topple over. The rectangle topples here, the triangle topples here if there is no sliding. The rectangle topples here, the pentagon topples here, hexagon topples here, heptagon topples here, octagon topples here, nonagon topples here. So eventually this point of contact of small radius area A, of circular area A, it's continuously toppling over. So rolling is basically topple or turning over at every moment. Okay. Okay, as illustrated in figure 4.2.8 below, as I showed you in the figure, we can consider the circular cross section of a rolling object as consisting of a rectangular polygon of infinite size. So we can consider the circular cross section as a regular polygon of infinite size. So you see this the 3, 4, 5, 6, 7, 8, 9, 10, 11 and up to infinity, you get a circle. So a circular object is like a polygon of infinite size. Okay. Okay, so the physics of sliding just cannot be applied to rolling. So rolling is pole apart different than sliding, guys. So please don't apply the physics of sliding upon rolling. So forget about the physics of sliding and let's get into rolling. So just get ready for rolling according to the principles of Tahirian cosmology, my cosmology. Okay, so instead of the forces utilized in the physics of sliding. Okay, so this is the physics of sliding, guys. This is the physics of sliding. 6 forces, inertial and mechanical, tug of war between Tahirian inertial forces and Al-Khazini Newton mechanical forces acting on the sliding object, mechanical gravitational force or mechanical forces, reaction, friction, etc. Gravity, blah blah. Okay, acting on the sliding object, sliding down an inclined plane. So 6 forces acting in sliding. Okay, guys, as I said before, that the physics of sliding is pole apart different than the physics of rolling, but both of them have the same essence of inertial forces. Okay, I'll go step by step. I don't want to jump too much and leave you behind. Okay, let's go read it like a story. So instead of the forces utilized in the physics of sliding, we will use the torques associated with them with the addition of another force, which will simply make the concept of the summation of forces in a particular direction equal to 0 invalid. Okay guys, this is very important to understand. Here I said that in the physics of sliding, which consists of 6 forces, we will add another force. Okay, so what is that force? That force is this force. This force, guys. Fayaz-Tahir field equation 1, or general field equation of all motion in the 7 heavens and 7 earths. Okay, so this is the force, guys. dm, this is the differential elemental version of the above equation. This equation is the differential element version. So instead of m, we multiply with dm. So this force dm r d square theta over dt square is added as a 7th force. Is added as a 7th force. Here, look. So we got this. This is not the force. This is the r. This is the differential element of mass, and this is the point of topple over a. This is the point of topple over a, where the rolling ball is toppling over. Okay, so this is the a. So this r is the distance of the any arbitrary random differential element of mass from the topple over. Okay, so on this dm, this force is acting dm r square d theta of d. This is the 7th force. 7 forces in the friction of sliding. There is no topple over, so 6 forces act. But in the physics of rolling, this force acts. Guys, when this force acts on this object, now we cannot determine the angle that this force makes with the horizontal. We cannot determine that angle. So the concept of the summation of forces cannot be applied on the physics of rolling, because otherwise the equations will never be solved. Why? Because the direction is random direction. We have randomly chosen that differential element of mass inside the geometrical shape of the body. So this force makes the concept of the summation of forces in any direction invalid. That's what I said here. That's what I explained. We will use with addition of another force that I just showed you, which will simply make the concept of the summation of forces in a particular direction equal to 0 invalid, because we don't know the direction of that force. So the torque associated with frictional force will be 0, because the summation of torques will be done at the point of toppling. Just forget about this, I'll correct this. But this is correct, but it's not in the right place. Okay. However, friction force does assist the body to topple and prevent it from sliding. Frictional force does assist the body to topple and prevent it from sliding. Okay, the moment due to the reaction N is equal to 0, because the point of toppling lies on the line of action of the reaction force. Similarly, the moment due to the torque, due to the torque that we shift in line of action of other forces of the force of friction will be 0, because the friction force passes through the point of topple over. So the torque due to the reaction N and friction force are both 0, because they both pass through the point of topple over. Their line of actions pass through the point of topple over or turning. Okay, the applied mechanical torque is the torque applied by the rectangular component of the weight of the sphere. So the only torque that causes motion is due to mg sine theta, mg sine beta, as I previously told you. So this is what I already told you. The inertial centrifugal torque is supplied by the Fayaz-Tahir inertial force, which will assist the opposing mechanical torque due to the flattening of the spherical body at the point of contact with the curved surface below, which will be the cause of the eventual damping of the perpetual motion otherwise. Guys, this is extremely important to understand. If this resisting torque, the inertial centrifugal torque, is supplied by the Fayaz-Tahir inertial force. Okay, now what is Fayaz-Tahir inertial force? Guys, here. This is, you know, this Fayaz-Tahirian inertial force, centripetal force couple. Okay, so guys, what happens when this is another way of writing this. So these two are the same, and these two are the same as well. Okay, so when you compare this one with this or this one with this, you get gravitation, which is primary gravitation. Binary star systems, two body motion. Okay, so when the particles get into touch with each other, they start touching each other, then they give rise to reaction and friction. And then this breaks up into mg or mg sine beta or mg cos theta. So then this is called secondary gravitation. Guys, secondary perturbation theory is not secondary gravitation. Perturbation theory is the same as primary gravitation. Why? Because in perturbation theory, Venus, Jupiter, Saturn, Uranus, Neptune, Pluto don't touch Mercury. Similarly, in binary star systems, one star does not touch the other star. So perturbation theory is included in primary gravitation. It should not be included in secondary gravitation. It's false to call perturbation theory as secondary gravitation. Secondary gravitation happens, guys, open your ears and listen to me very carefully. Secondary gravitation happens when two bodies start touching each other. And then this is astronomy, GMM or R square, primary gravitation, astronomy. These 1, 2, 3, 4, 5 are synonymous. Then when the bodies start touching each other, it becomes physics. Now guys, listen to me very carefully. Allah Kareem, the Supreme, the Lord of Muhammad sallallahu alaihi wasallam. Allahumma salli ala Muhammadin wa ala ali Muhammad. Kama sallaita ala Ibrahim wa ala ali Ibrahim. Innaka Hamidum Majid. Allah Kareem created the astronomical bodies. Now, the physics that determines the motion of the astronomical bodies is behind the physics that determine the motion of bodies on the surfaces of these bodies. Let's say Earth. Earth is revolving around the Sun. Sun is also revolving around Tahir center of rotation with a very small radius and a very small speed. So they are in kind of binary with each other, even though there are other planets as well. But just take the example of the Earth and the Sun. So they are kind of binaries, two binaries. Even though the motion of one of the binaries is very small, like that of the Sun. Okay, so the physics that determine the motion of the Sun and the Earth is called astronomy because they don't touch each other. But when on the surfaces of the Earth, when objects start touching each other, then it becomes physics. And the physics behind physics, or the physics of those bodies on the surfaces of planets, is basically astronomy. The physics that govern the motion of the planets itself. So humans could not understand astronomy properly. So that's why they could not understand physics. Why? Because behind physics is the science of astronomy. If the fundamental principles of Fayaz-Tahir, of astronomy, cannot be grasped or understood, then physics simply cannot be grasped or understood, because the DNA of physics lies in the DNA of astronomy. Okay, so when this centrifugal force breaks up, when bodies start touching each other, then this the gravitational the force that comes into opposition to gravitation breaks up into two components, mv square over rho and mdv over dt. They both are perpendicular to each other. When they are together in primary gravitation, it's in line. Both the components are in line. But when they break up in physics, then they become perpendicular to each other. Okay. Okay, so this force I was talking about, mv square over rho and mdv over dt. So the centrifugal, the Tahirian centrifugal force of the binary star systems breaks up when it comes to physics, because this is touching some inclined plane and the inclined plane is touching the surface of a planet, suppose Earth or Mars. If the experiment is done on Mars, then it's Mars. If it's done on Earth, it's Earth. If it's done on some other planets, then it's the planet. Okay, so the centrifugal force breaks up into mdv over dt and mv square over rho. Now, this inertial force is opposing along with mg cos beta. Inertial forces either oppose alone or assist other opposing forces like mg cos beta. Now, this torque produced by this force mg cos beta resists the motion, and similarly mv square over rho resists the motion. If these two torques, they don't resist, then this will keep on rolling forever. Or if it's rolling on a cycloid like this, then it will come at the same level, then it goes back at the same level. So it will be a perpetual motion machine if these two components, they don't give a resisting torque to damp the motion. That's what I said in that paragraph. Okay. Torque due to the flattening of the spherical body. Flattening of the spherical body, the area in contact with each other. This area in contact with each other, which gives this moment arm, the small moment arm. Okay, we will consider this later here on Wikipedia. If you go to Wikipedia and write contact mechanics, you will see the contact area, this of circular area of radius A. But this analysis is done stationary when this ball is not rolling and with the force acting on the ball. But I will consider it the weight of the ball as the force being applied. So I will make a little bit change. Okay. Okay, so guys, you see, in rolling, the direction of n changes little bit to the right. In sliding, it's perpendicular to this component mg sine beta, but in rolling, it's little bit, because rolling is toppling, so the point is toppling at here, at this point A. This point A. So this is the direction of the reaction, normal reaction. This is the direction, little bit on the right of the one in sliding. Okay, but force is the same. Okay, this force is the same, mdv over dt. This is the force of friction. This is mg cos beta, mv square. Forces are the same, except this force is added. When this force is added, because of the rolling, this force is added. And from where is this force added? From Fayaz-Tahir in field equation. Fayaz-Tahir field equation. This field equation. This force is added. dm r d square theta over dt square. This part will be 0 because dr over dt is 0. dr over dt is not changing. So this is the force. When this force is added, so force is the same. 1, 2, 3, 4, 5, 6. 6 forces in sliding and 6 forces. 1, 2, 3, 4, 5, 6 and the 7th, this force. 7 forces, inertial and mechanical, acting on the, this is also inertial force. This is also inertial force. Now the line of action of this force is random. We don't know. So this, what angle it subtends with a particular direction, we don't know. So we cannot apply the summation of forces concept here. So what we will apply the summation of torques here. Okay. Hope you understand. Okay. So eventual dampening of the perpetual motion otherwise. So I already explained this to you. Tahir centrifugal torque assists the resisting Tahir centrifugal torques. So Tahir centrifugal torque mg cos beta times A assists the resisting Tahir centrifugal torque mv square over rho. So both of them assist each other. These two are the resisting torques that resist the perpetuality of the motion. Like if it's rolling on a cycloid, then it will eventually dampen like this because of these two torques. So this torque is the cause of the motion and these two torques cause of the dampening. This also dampens. This also dampens mdv over dt. So this is also the cause of the damping, of the stopping of the rolling disc. Okay. in opposing rolling, just as in sliding, the Tahir centrifugal forces assist the frictional force in opposing sliding. Very simple, guys. Okay. Rolling of object of circular cross section is shown to be continuous turning or toppling at each moment. I already explained it. Okay. Now, here from the rectangle, we will come to here, polygon. Polygon of how many sides? Applied and resisting angle torques and multi-sided regular, as I call it, multi-sided polygon. Okay, so you see, we like whatever the contact area is here, this 2A is here, A plus A, 2 radii. We describe the polygon accordingly. Easy, not too difficult. Okay, so this is the alpha that the circular area subtends at the center of the ball. So this angle is alpha by 2, this angle is alpha by 2. Okay, so this distance is A, which is equal to r sine alpha by 2. This distance A. This distance A. Okay, good. Okay, this figure is important, guys. Okay, so torque is mg sine beta. This is not the actual. This is just in continuation to the figure diagram that I showed you here of the rectangle. Just a continuation. This is not the actual one that we are going to use. The actual equation is a little bit, because forces are more, like 7 forces. So the 2 of the torques will be 0. So we will have 5 forces, 5 torques in the final equation. Just get ready. Okay. Okay. So now from the rectangle we went to the polygon, multi-sided polygon, and eventually we will come to the circle, because we are going to we are going to decipher the motion of a ball rolling down a cycloid. So this is our goal. We want to find the time it takes to reach the bottom of the cycloid. Okay. So guys, so you guys, the radius r, this is the point B. I don't know why I put this point. Okay, so this point is A, the point of topple over. Okay, mg cos beta is this component, and I haven't seen the component mv square. I haven't seen the other forces. Don't worry about it. And just this is very simple. The analogy of the 3 figures, figure 4.2.10. Applied and resisting mechanical torques on the sphere, inertial torques, the resisting torque. Okay, forget about this. Don't worry. Inertial torque shown in due to Tahir centrifugal forces shown in figure along with the, but this is true, this torque, this one is the inertial torque. But I'll show you what that torque is here. Okay. Okay, the Tahirian condition for rolling, toppling to just start is, so this is the condition, beta should be greater than alpha by 2. So beta, if this angle beta is greater than alpha by 2, then this body will start rolling. Now let me drive the equations of rolling once and forever in the history of the Tahirian cosmology. Let us suppose a solid sphere of radius r rolling down a curved plane as shown in figure 4.2.8 and 4.2.9. Also just focus on 4.2.9 is this. Okay, so 4.2.8 is this. So I already explained it to you. Okay. Okay, it is evident from the figure 4.2.12, this figure of pure rolling, that the concept of summation of forces equal to 0 in a particular direction cannot be applied due to the unknown direction of the total inertial force associated with differential element of mass dm of the spherical rolling body. Now this is the total inertial force. When we integrate, we get the sum, the total. So now where does this force? No one knows in the universe where this force is acting. So we cannot apply summation of forces because we cannot find its component in a particular direction. Okay, so we need to apply something else. So we must apply a different concept such as the summation of torques. Why? Because is equal to 0 in any direction, either clockwise or anti-clockwise. Why? Because we know where the point and the distance is from the point of topple over of all the forces. For these forces R and these forces we already know. Now these two forces, the force of friction and the normal force, not the normal force, but the reaction force, passes. It's not normal, it's not at 90 degree. So, but I retain the letter N because I use the letter N here in sliding. I use the letter N here in sliding, so I retain the letter N, but here does not mean normal because it's not at 90 degrees, passing from the point of topple over. Okay, so this point passes from the topple over, this force passes from the topple over. So the torques, because of N and mu and are 0. So there are total 7 forces. So we will consider only 5 forces in the final equation that we will battle. On the contrary, the direction of all the 6 forces in the scenario of pure sliding are known as below, because there is no rotation due to no toppling. Okay, in toppling, in sliding, we know the directions of all the 6 forces. Therefore, the condition of torques cannot be applied here. So in sliding, there is no toppling. So the condition of torques cannot be applied because we don't know their turning distances, the lever arm distances, or whatever you call it. Therefore, the condition of torque cannot be applied here on sliding, because the toppling in the case of sliding is unknown, so we cannot apply the condition of torques. And in rolling, the movement of arm of one force is unknown, so we cannot apply summation of forces. The only condition that can be applied is the condition of sliding. Summation of forces in any direction equal to 0. Because the toppling is random, is not defined. So we have to apply the summation of forces in any direction equal to 0 in the case of sliding. The torque associated with shifting mu n in line with other forces is therefore unimportant. So when we shift this friction force from here to here in line with this force, Tahir inertial force, centrifugal force, these are parts of centrifugal force. This centrifugal force, which opposes the gravitational force, which is centripetal force. So these two have the essence of this one. So this centrifugal force converts into 2 centrifugal components. This is the centrifugal components. This centrifugal force. This is the force when you drive your car in a straight line. When you accelerate, you are pushed back. You are pushed back with this Tahir centrifugal force. Centrifugal force does not have anything to do with a center or a radius or a blah blah blah. But why? Of a circle. But it does have a center of rotation, Tahir center of rotation. But not in the case of all the time in the case of a circle. The torque associated, but if the body is moving in a circle, then its direction is in opposition to the direction of the center of the circle. The torque associated with shifting in line with the other forces, they are unimportant. The sliding torque is unimportant. So we can add a torque here like this. But it will not be considered. So we can shift this force here and do the summation. 6 forces act. It is evident from figure 4.2.13 of pure sliding that the concept of the summation of torques is equal to 0 in any direction cannot be applied due to the unknown direction of toppling of the sliding body. Now the sliding body's toppling is unknown, so we cannot apply the condition of torque. We don't know which point is the point of topple over, so we cannot apply torques. Even if we apply the torque here, it doesn't make any sense because there is no toppling in the case of sliding happening. So useless. Okay, so I have already explained this. This is Tahirian centrifugal force. This is another version of the Tahirian centrifugal force. Okay, so this is gravitational force, Al-Khazini Newton gravity. I hate to write it like this, but since you are afflicted with the calamity of misunderstanding of writing this capital M, I hate to write this in the form of capital M. This is one of the places that I've written here because you are inflicted with this disease to write it G, bigger M, mass of the earth and the mass of the object. Highly misleading, but still I leave it because you are familiar with this contagious disease in your minds. Okay, so here mg sine beta You see, there is no big M in physics. It's only in astronomy. But you apply it on physics and mix up everything and end up with 0 out of 10 or 100. Okay, so this is the essence of the universe, guys, of the 7 heavens and the 7 earths. Fayaz-Tahir field equation, 1, or general field equation, 1 of all motion. Guys, remember in one of my videos I told you that I will solve everything in the 7 heavens and 7 earth with this one. Remember? I showed you in my previous videos. Okay. So this problem can be easily understood with this. If you understand my previous videos and use this one and this one. This is astronomy, binary star motion. This is astronomy, guys, binary stars. And when it breaks up into physics, you see this, the body rolling down the cycloid. This is okay. I have still kept my promise. Okay, guys, you can see my previous video, and the videos are not that good. Hopefully I will download them once again in a better fashion. Okay. So the only difference is the Tahirian inertial force associated with the differential element of masses between pure rolling and pure sliding, which eventually forces us to choose between the concept of summation of forces and the concept of summation of torques, of the two summation of forces and the concept of the summation of torques. Okay, so guys, now you need to go to Wikipedia and write contact mechanics on Google or any other search engine. Then it will take you to Wikipedia, this site, and you can see the derivations. The radius of the contact area is given on Wikipedia as below: r sine alpha by 2, which is a r sine alpha by 2. R sine alpha by 2 is a. So this is the a circle of contact, small circle of contact of radius a. This is a, this is a. So r sine alpha by 2 is this distance a, which is being multiplied with mg cos beta with the resisting torque. And this distance is r square minus a square, square root r square minus a square, the other adjacent side of the right angle triangle. Okay. Where were we? Okay. So you can go to Wikipedia. Okay. The radius of the contact area is given as below. So this is from Wikipedia, guys. You need to understand this from Wikipedia. I don't want to go into the details of this. It's related to theory of elasticity of materials or theory of elastic stability. Okay, so F is Fmg cos beta. Okay, guys, on Wikipedia they have done the analysis, the static one, no dynamics. So in my analysis, I won't add plus mv square over rho like this force. I won't add mv square over rho. Why? Because they have done the analysis for the static case, mg cos beta, mg on a straight horizontal plane. But we are going to do the analysis of the mass rolling down along the cycloid. So we will take the component of the gravity, mg cos beta. So I have taken F is equal to mg cos beta. Okay, guys, next, the signs are very important, extremely important. Otherwise, you would never get to the answer. You get the wrong answer. Okay, when we slide a ball or a sphere on a cycloid, cusp of a cycloid like this, and the origin is here. I have kept the origin here. And the equation of the cycloid like this. Like this is y-axis, positive y, this is positive x-axis. Okay. So when the body comes down here, then the angle beta here is more than it's here. So the change in the angle beta is negative. Distance is positive. The distance it travels on the cycloid is positive, but the change in the angle is negative. Rho is always positive. For a cycloid, if you calculate, I will calculate it, I'll show you. If you calculate, it will always be, the rho is the rho of the radius of the cycloid. Rho is always 4r cos beta, 8 cos beta. R is the radius of the generating circle, which is 2 meter. R is the radius of the generating circle that generates the cycloid. I have taken it 2 meter. So all are in S system international, MKS system, meter, kilogram, second. G is taken to be 9.81 meter per second. Okay, we'll come back to it later. Okay, so where F is equal to mg cos beta dA. So I ignored. Why? Because they have done the analysis static, no dynamic, no velocity. So I will not add this component. I will just take this mg cos beta. Okay, keep this figure in mind for rolling. Figure 4.2.12. Reaction is in the direction of AC as in figure 4.2.9. AC direction. Reaction is in this direction. But I have still kept the letter N, though it's not normal. Okay, let's, therefore summation of torques give us, finally we will apply the summation of torques is equal to 0, no net torque. In Tahirian cosmology, guys, systems are in equilibrium even under extreme conditions of torque. Okay, I won't go into the details of it. Otherwise, you need to read a lot of things to understand this. Okay. Summation of torque A is equal to 0. This deals with the part of the universe that is still under formation, that is still being formed. But we are talking about the well-formed part of the universe, the surfaces of the planets, or the planets revolving around the sun itself, the mature part of the universe that can be defined with the principles of Tahirian astronomy, or Tahirian cosmology, or Tahir cosmology. Okay, so we do summation of torque, we obtain mg sine beta minus m dv over t into r cos alpha by 2 minus this force minus m. This is easy, guys. You can do it from this figure. You can easily write it down. The torque due to this force friction and this force reaction, though represented by n, is 0. So turning moment are taken at the point of topple over A, because all distances are known. Okay, so here you can usually, like the way you already do, you can easily convert it into like this. Okay, so you simplify mg sine beta or cos alpha by 2. Don't want to go into the details of this. This is easy. Okay, so you open up this and then you do a little bit change here. This is the angular velocity. Okay, let me tell something about the angular velocity. Guys, listen to me very carefully. Okay, this is not that clear. Okay, let's go to this picture. Okay, guys, this is rolling down. Okay, this is AC. Okay, now let's say the differential element is here. This differential element of mass dm is here, somewhere here. And now connect this with the line with the point of topple over r. The moment of inertia will not be centroidal. Centroidal would be with respect to this. But here the toppling is not happening here. Toppling is happening here. So we'll take the moments of the force with respect to this point. And when with respect to A, then the force is perpendicular to it, the R. The force is this force, I have drawn the rectangular box to show that this force is perpendicular to the distance R. Always. Here. Look. Sine beta, cos beta at 90 degree. This force is perpendicular to, always perpendicular to the point of topple over. The point of topple over where the rotation is happening. Okay. Okay, I was going to tell you something very important about angular velocity. Okay, guys, look. The dm is here. Draw a line and connect it with point A and make it R. Now draw another line parallel to this line R from the center of the circle like this. Now when the circle rolls, this line rolls with the usual angular velocity, and since this line is parallel to this line, it means this line R also rolls with the same angular velocity omega. So this line rolls with the same angular velocity with which the circle is rolling. Why? Because any diametrical plane parallel to this line passing from the center, diameter passing from the center, is rotating with the same angular velocity as this line. So this angular velocity is the angular velocity of the rolling object. This angular velocity is the angular velocity of the rolling object. R square dm mg cos beta r sine alpha by 2 minus mv. Okay, this is easy, guys. So this is the moment of inertia. But here I would like to clarify that in Tahirian cosmology, this is not moment of inertia. This is the second moment of inertia. In gyroscopes, I will introduce you with RDM, integrate RDM, which I have called first moment of inertia. That's a different story. When we do gyroscopes, we'll discuss it, inshallah. Okay, so you come here to the torques due to n and mu n are equal to 0 because their line of actions pass through the toppling point, or at least assume to be passing from there. Even if they don't pass, just assume it passing from there because they're very close. Okay. Okay. Now, r cos alpha by 2 is equal to r square minus a square. Guys, here, this is the gist of my calculations. Okay. Okay. So, this distance is, this is the right angle triangle. This one. So, this is r, this is a. So, this distance is r square root of r square minus a square, which is multiplied with this to get the applied torque, the torque that triggers the motion. The only force that triggers the motion is this force, guys. Out of the 7 forces, out of these 7 forces, this is the force, only force that triggers the motion. It's not difficult, it's easy, because the angle of the incline. Okay. Okay, so guys, here what I have done, I have considered the higher powers of a square, a cube, to approximate, to make life easier for you guys and for your larva, generation. In other words, I have basically ignored higher powers of a. So I will deal with a only, but not with a square, a cube, a. Okay, so ignoring a square, we get r. So omega r square is v r omega r. In other words, I have basically ignored. Okay, so very important, guys, very important, very important. Keep it in mind and take every else junk out of your mind. Okay. Okay. M dv over dt, the same thing, becomes like this. Just play around with it. Okay. Okay. So eventually you do this here, apply chain rule here. Okay. Okay, guys, this is homework. This is your homework. Okay, guys, remember ds is equal to minus rho d beta. You have to apply it again and again with the negative sign. Don't apply it with the plus sign. Okay, so VDM. Okay, guys, this I is not the centroidal. This I is the centroidal for the sphere, which is 2 over 5 mr square plus mr square. This I is not the centroidal. Centroidal for a moment of inertia for a sphere ball, solid ball, is 2 over 5 mr square. But here this is not centroidal because we are not taking the moment of inertia, second moment of inertia, with respect to the center. We are taking with respect to a point on this surface of the ball. You can check any engineering book or physics book or second moment or moment of inertia. They won't say second moment of inertia. It's only me who say that. Who can say that? Okay. Okay, guys, here is one more important. You might know from calculus when you did iterated integrals, multiple integrals, that if z is can be integrated with respect to x while holding y constant, only if z is an explicit function of x and y. Similarly, z can also be integrated with respect to y while holding x constant, only if z is an explicit function of x and y. When we solve multiple integrals to find volumes or other things, or in general, then we apply this condition and we get correct answers. So we can apply the same condition, but the essence behind it is that x, similarly, because nature is explicit, guys, similarly z can also be integrated with respect to y holding x constant, only if z is an explicit function of x and y. Similarly, FVB is an explicit function of v and b and can be integrated with respect to b while holding v constant. Moreover, our nature is explicit and so is the Tahirian function. Okay, so you guys, you see, we held v constant, we take it out and integrate it with respect to beta. You see this? You see here, because it was an explicit function of v and beta, so when we integrated with respect to beta while holding v constant, so we took v out, like you do in iterated integrals when you find volume of surfaces in calculus. Now let us solve the two integrals one by one as follows for a cycloid curve. So now we will utilize the characteristics of a cycloid curve. So these two, we need to solve these integrals. If a is 0, so you see you get the ideal case. If a is 0, you get the ideal case when the bodies don't touch. So but that becomes astronomy. That does not stay the physics. So you see, you describe a cycloid with astronomy. You describe physics with astronomy. You basically not describing the motion of a cycloid. You are describing motion of planets and saying that we are describing a cycloid. Bullshit. Now let us solve the two integrals one by one as follows for a cycloid. Okay, but the real and the ideal cases are very close, so that's why the a value is very small and these values are very small. So let's see what we see. Okay, so blah blah blah. This is exercise, guys. Homework. This is your homework. You know, you have to do the homework now. A lot of homework, guys. Lot of homework. So these two integrals, blah 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 blah. Okay, so a is blah 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 blah. Mass of rolling sphere. Okay, so I have considered the rolling sphere made of steel and the surface of the cycloid of plastic. So the cycloid is plastic and the rolling sphere is steel. So just arbitrary values of, but not arbitrary. I mean random like, but they make sense. They make sense. They make sense and they're real. A ball can be made out of these values. R is equal to 2 meters. This is the radially generating circle that generates the cycloid. So E is the modulus of elasticity for steel, 2.1 times 10 to the power 11 Newton per square meter. Modulus of elasticity is also called Young's modulus of elasticity. For plastic is 2.75. For plastic is less elastic and steel is more elastic. So equivalent, the E equivalent is given by this, where V1 is the Poisson's ratio. Poisson's ratio for steel is 0.3 and Poisson's ratio for plastic is 0.38. The radius of curvature of the cycloid is rho is equal to 4r cos beta. R is 2, so 8 cos beta. Okay, the equations of the cycloid that I am going to use, x is equal to r2 beta plus sine 2 beta, y is equal to r1 minus cos 2 beta for cycloid. So you differentiate, you get this. Also, don't forget to put the sign minus d beta. 4 sine 2 beta d beta. Okay, so dy is also negative, guys. Dy is also negative. Why? Because the ball is, y is like this. When the ball comes down like this, the final value is lower. So the smaller value is smaller and lower. Smaller value minus bigger value, it will give you minus. So signs are very important, guys. If you make a mistake in signs, then you won't be able to get to the right answer. Okay. So R equivalent is given on Wikipedia under contact mechanics. You can find it. So 8R cos beta, 8 cos beta. The radius of curvature of the cycloid and the radius of the circle, of the circle R. So 1 over equivalent is E equivalent is this, and F is mg cos beta. Because it's static, so I won't add the component plus mv square over rho, because they have done the analysis of a static indentation mark on both the surfaces, where beta is less than or equal to 0 and less than or equal to pi by 2. So I is not the centroidal 2 over 5, but it's the centroidal plus mr square, which is 2 over 5 plus 2 over 5 mr square plus mr square, which is 7 over 5 mr square. Surface is considered made of plastic and the rolling sphere made of steel. The surface of the cycloid is considered made of plastic and the rolling sphere made of steel. Okay, guys, you do this homework. Now using the substitution, u is equal to cos beta and plus du is equal to minus sin beta minus d beta. Sign again, guys, over and over again. Minus sin beta d beta. Okay, so this is exercise, homework, guys. So this is your homework too. Now to solve the above integral problem, we need substitution. Okay, guys, in order to solve the integrals here, these integrals here, we need substitution. These integrals. Okay. The best way to look for a suitable substitution is to see what my Fayaz-Tahir series expansion functions do to the binomial expansion as follows. Okay, so this is my Fayaz-Tahir binomial series. Sorry, Fayaz-Tahir series expansion function. You might have seen it in my video. So what I will do is to use, I will further upload a lot of videos on it soon, inshallah. So what I will do is to use fx is equal to 1 plus ax to the power minus n. So I will substitute this function here in my series expansion, in Tahir series expansion of functions above algorithmic functions. The result is a natural selection. We will see. Okay, so exercise, homework, guys, again. F prime x, f 2x, these are the derivatives. Okay, so we put them back here, dividing both sides by 1 plus ax minus 1. Get this, rewriting the above as below, so we get this. Transposing terms, we obtain Fayaz-Tahir binomial theorem as below. So this binomial theorem is not Umar Khayyam's binomial theorem, like the one you are already familiar with. So this theorem is, binomial theorem is called Fayaz-Tahir binomial theorem or Tahir binomial theorem. You must not have seen it before. Okay, 1 plus ax to the power n is equal to this. You can write it in a compact form where the range of x should be minus 1 over 2a. I won't discuss about this binomial theorem's characteristics and its superiority over Umar Khayyam's binomial theorem or its equivalence with the other binomial theorem here, but I will upload another video. The above is the condition for convergence of the above series to a finite value. So if this holds, then it will converge to a finite value. Its convergence is very high, very big, not like the Umar Khayyam's binomial theorem. Okay, where n, k are the rising factorials, very natural factorials, rising factorials, very natural. Given by n, k is equal to n, blah, blah, blah. And n naught is equal to 1, n1 is equal to n sub 1 is equal to n1 term, 2 term, where k is also the number of terms in the expansion of the rising factorials. Now put t is equal to ax over 1 plus ax in the above binomial series and see what it gives. It gives you this, t less than 1. This is the binomial, Umar Khayyam's binomial series. If you do the substitution here, it will give you Umar Khayyam's binomial series. Okay, guys. So where ax is equal to t over 1 minus t, there are basically two rising factorial forms of the binomial series. Either you can keep the signs of n and t in the rising factorial form or change the signs of n and t in the rising factorial form on the right. If one is positive, make it negative, and if one is negative, then make it positive. This is also very important. Otherwise you cannot solve the integrals if you don't understand this. I don't want to go, it's all mathematics, don't want to go into banana. So we can clearly see that the substitution is a very Islamic natural one. As you know, Islam is fitra. Fitra means nature. So this I call it the natural or Islamic substitution because it's very natural. One provided to me by only by the Lord of Muhammad, peace be upon him, sallallahu alaihi wasallam. Allahumma salli ala Muhammadin wa ala ali Muhammad kama sallaita ala Ibrahim wa ala ali Ibrahim innaka Hamidum Majid. Allah Kareem, the Supreme, the Lord of Muhammad sallallahu alaihi wasallam. So in line with Tahit series expansion of functions, I will use the substitution as below. T is equal to 400u or 1 plus 400u over this integral, or the other type of integral. The other one will also contain the same kind of things. So we will apply the solution here, substitution. Okay guys, signs very important. Keep this thing in mind. Signs are very important. Negative signs will be introduced as before. Signs very important guys. Without signs, no life. So du is equal to minus 1 over 400, 1 over 1 minus t whole square dt. Okay. So you have this, blah blah blah. Now I will write the above binomial term in terms of rising factorials as below. Guys, here is the turning point. There you should know how to write it in terms of the rising factorials. Okay, here. Okay, from here. This is all exercise, guys. Homework, exercise. So you have to take short screenshots so that you understand. It took me a long time to get to this. Okay, so all calculations, homework. So we get this structure, with this kind of structure. I forgot what is this called. Did it long time ago. This is hypergeometric series. So this is, we bring this, if we have something like this, then we can write it in Gauss hypergeometric series like that, where alpha is not equal to minus 1. Okay, so because if we write it in hypergeometric series, then Wolfram or Math GPT or Chat GPT or other AIs can easily solve the integral. Or Microsoft Copilot or Gemini. Okay, so we get this one in terms of summation and hypergeometric series, Gauss hypergeometric series. Okay, so this is just mathematics, right? Also you write it like this. In a similar fashion I can solve the other integral as below. Okay, I can solve the Ahmed yaar zara main kar raha tha. In a similar chalo kar lo. In a similar fashion I can solve the other integral as below. Thank you. Okay, so integrate, guys, this is all exercise, homework. So be careful, signs very important. No life without signs. Okay, so this is this, this is this, this is this. Now I will use the substitution as below, so now I use the substitution. Signs very important, guys. Negative sign will be introduced as before. Du this, okay, so you get this, this. Now I will write the above binomial in terms of rising factorials as below. Oh, so we write in terms of rising factorials. Where did I write it? Okay, anyhow, that's what we get. So we write it in this form with the hypergeometric series. Okay, so all exercise, guys, mathematics. Don't want to go into the details of this. Okay. Okay, so we get this hypergeometric series. So get this. So putting the pieces of the puzzle together, I obtain as below. So we had this main equation. So when we put it everything back, we get this. We get this. So original one is this, and these two terms are added. This is S1 term, S1 beta. This term is a function of beta. Similarly, this term is a function of beta. Only beta is variable here. Only beta is variable here. So this one is S1b. Okay, putting the boundary condition where v is equal to 0 and y is equal to 4, I obtain as below. So y is for the top of the cusp of the cycloid, this top. If the cycloid is like this top is here. So this is 4, y is 4, x is 2 pi. As in my all previous videos, you can check there. Obtain as below. The y-axis here, x-axis here, and the cusp of the cycloid goes like this. This distance is 2 pi meter and this is 4 meter. So when we put the spherical ball here, then velocity is 0 and y value is 4 meter. I obtain as below. So c value you can calculate. This c, the constant of integration, you can calculate 8m g r square over I plus m r square. Okay, so we get velocity is v square. This is the equation that we get. Okay. Time taken to roll down a cycloid is then given as below. It's pi by 2 to 0 because the angle beta is here, pi by 2. Here beta is 0. So goes pi by 2 to 0 minus ds over dv. ds is positive. But when you put 1 plus dy over dx whole square, then you get a negative sign here. This negative sign changes the limits. ds is positive as I took before. But when you further expand it in terms of the differentials, dx, 1 plus square root of 1 plus dy by dx whole square dx, you get a negative sign here, which eventually changes 0 pi by 2. So here ds is positive, 1 plus square root of 1 plus dx. But actually there is a negative sign here. Check my previous videos how I got that negative sign. Okay, so the time taken is this. Just plug in the values. If this is velocity, this term divided by this is v. This is from dy by dx. For this cycloid, if you divide dy by dx, you get tan inverse tan beta. So dy by dx is equal to tan beta when you divide by this. So here we have 1 plus tan square beta, 1 plus dy by d whole square tan beta. This is also a natural selection of the cycloid. Okay, so you have this one. So you have this one. You know the values of A, R, M, R. So I is 7 over 5 mr square, not 2 over 5 mr square. It's not the centroidal. It's the other one. You can use parallel axis theorem for moment of inertia. And get okay. So this one is okay. So this one is the time taken for the spherical ball to come down, slide down from the cycloid, from the the top part of the cusp to the bottom part of the cusp. Okay. So if you use using high precision mathematics, I obtain a value of. You can use Wolfram. You can put it in Wolfram. I didn't put it in Wolfram. I put it in MathGPT, ChatGPT, and Gemini. They all give, all the three, they give 2.20945 seconds. So approximately 2.20. So this is the time that the ball takes to come down to the bottom. 2.2095. Okay, here comes the deal now. Okay, this is another way of writing it. S1 beta, because these terms, they are function of beta. So you can write these terms like S1 beta, like this, S2 beta is equal to another term. So Z is also the argument of the hypergeometric series is also a function of beta. In the hypergeometric series here, this argument is also a function of beta. The time taken for the spherical ball in the ideal case is as below. Now we will compare this time that we have found, 2.20945 seconds, with the time, with the real case where there is no resistive torque, there is no radius of contact. Astronomy. Using astronomy to describe physics. Bullshit. The time taken for the spherical ball in the ideal case is as below. I hate to do it, but just to explain it to you, is this. So the difference between the real with rolling resistance and the resistance free ideal case is 1/100th of a second. Now guys, this is the main final paragraph that you need to understand. The entire purpose from the beginning to the end of all these remarkable calculations in Islamic history was to prove that the gap between theoretical perfection and physical reality is nearly non-existent, very small, non-existent, very small, 0.0119. Specifically, the difference is as tiny as 1/100th of a second, 1/100th of a second, a margin so slim that it cannot be detected by the human eye or even the most precise scientific instruments due to human error. Instruments can detect if there is no human error, but human error cannot be avoided during the experiment. Because this discrepancy is so minute, the actual movement of a ball rolling down a real world cycloid ramp appears identical to the movement of a ball on a perfectly resistanceless S1 beta and S2 beta is equal to 0. Ideal cycloid, a tautochron. Essentially, the mathematical ideal and the physical real are so close that any remaining difference likely disappears within the natural margin of human perception and experimental error. Now let me do some calculation for the case of the cycloid to behave like a tautochron in the ideal case without elastic resistance. We will write the velocity. This is just to show that for the case of a cycloid, without elastic resistance or the elastic torque, resisting torque, it behaves like a tautochron. Tautochron means wherever you leave the ball, it will reach the bottom with the same time that it reaches from the top to the bottom. We will write the velocity of the ball rolling toppling down along the cycloid at any arbitrary point as below. This is an arbitrary point. We are going to put it anywhere in between, where beta is greater than 0 and less than pi by 2. So v square is this. We consider any arbitrary point on the cusp of the cycloid, say y0 given as blah blah blah. Okay. Okay, at y0, v0 is equal to 0. So wherever we put the cycloid, the velocity is 0 as before we use the boundary condition. The essence is the same because we let it go from rest. We put it and then let it go from rest under the action of gravity. So the equation becomes as below. V